So yesterday we have started with a new chapter. It is on mechanical properties, and in this chapter, basically we have addressed a few, definition, from our lecture yesterday, which is actually on stress, strain, elastic behavior, and plastic behavior. So types of stress and strain, it can be categorized into four. We have tensile. If you still remember, for tensile, it means that you have a load or maybe a force that has been pulled, which cause elongation to the object. The second one is actually on compressive load, where you will see that the material has been pushed. You apply some force, and this force is basically shortening or altering the object, giving a difference in terms of the length and whatsoever. Third one is actually on shearing, strains or stress, where the force is applied at the side of the object. So you will see that the material will be tilted a bit, okay, and the resulted tilting will give some difference in terms of theta, or maybe the degree of the displacement. Okay, and finally, torsional deformation means that the force applied is actually rotating, which cause some variation in terms of probably like the diameter or maybe the angle of any objects that been stressed. Stress actually means that you have a force which apply as a unit of area. So this is actually very basic. You have learned this during your high school in physics, form 4. And you know that by definition, the formula is actually force F over area, and the unit, since you know that force is equal to Newton, area is equals to meter square, cm square, or maybe millimeter square, then unit can be in Newton over meter square or Newton over millimeter square, right? And apart from that, for stress, we have two different types, which one is actually, one of it is actually on the ultimate or the maximum stress that the materials can or the object can withstand, and finally the breaking stress, okay, where after it reach the ultimate tensile, it will experience necking, fracture, and finally break. Okay. So still for stress, we can categorize into four. We have tensile, compressive, shearing, and strain. I don't think that I will go this in detail from yesterday. But for strain, we know that this is actually the resulted deformation, hasil daripada perubahan daya yang dikenakan ataupun stress, tekanan yang dikenakan. Okay, so stress will actually resulted the deformation, the displacement, anything that will result a permanent changes is known to be related with strain as well. And strain doesn't have any unit, is dimensionless. Okay. And yesterday also we have been introduced with plastic and elastic deformation. So what does it mean, elastic deformation? As I said, elastic deformation, it means that you have materials that when you apply force, tensile, compressive, or whatsoever, the material can actually return to its original shape after you unload or after you release the force. So part of the example, you can have like ceramic, glass, composite, and whatsoever. And for elastic deformation, you can have linear elastic on non-linear elastic. Linear elastic, it means that when whatever amount of force that you apply, it doesn't give any changes. Okay. I think basic examples you have like ceramics, glass, and whatsoever. Non-linear is actually related with materials that it can elongate for a while, and then after that, when you release it, it will return back to its original shape. For example, like rubber band, spring, or whatsoever. Meanwhile, plastic deformation is more of a permanent deformation, where when you have, for example, polymer, plastic, metal, if the amount of force applied is actually greater, then metal also can experience plastic deformation. So what happens is basically the particles will have some effect in terms of like lengthening, I think separation and whatsoever, then cause a deformation produced during this I think process. So that is why when you release back the or unload the force, the material didn't return to its original shape. It has some defects or maybe some deformation. Dia dah jadi cacat sikit lah. Kalau you tarik you punya kawan punya pipi, kalau you tarik lama sangat, dia jadi panjang, lebih jadi macam gajah dah. Okay, so that is actually the things. And when you look at the profile, normally for plastic deformation, if the amount of force applied is actually very small, you will see that the trend is actually slightly linear. Dia jadi linear for a while, and then after that, when you increase the force, it start to experience bending. So this bending is actually with regards to the displacement or the deformation that resulted from the amount of load that you apply. Okay, and when you release back or when it reach the maximum, you release the force back, it will actually return or maybe goes to a value that is not the similar as the origin. So some basic I think formula for stress. I'm not going to go this in detail. And this is actually part of the testing that we did in mechanical testing. It is known as stress strain testing, and the instrument used to test is actually known as UTM, ultimate tensile machine. So this tensile machine is actually function to measure what will be the maximum tensile for a material that you produce. If you produce a polymer, if you produce a composite and whatsoever, if you want to check what would be the features, what would be the properties, what would be the mechanical strength of this material, you need to perform this test. So this test is actually not, I think, as simple as that. You need to follow a standard procedure. You need to follow ASTM, American Standard Testing Methods. You can also follow JS, Japanese Standard, BS, British Standard. Kalau Malaysia, MS lah, Malaysian Standard. Okay. But I think most of the standards acceptable will be following ASTM or probably BS and also JS. So you need to prepare your specimen in a dumbbell shape. There's a mold that you need to produce. And the result will be as follows. You can actually produce a profile, something like this, which actually can explain the behavior of your material. So if your material is actually brittle, for example, glass, so you will see that the profile of stress-strain curve is actually going to be linear. But if you have something that is non-linear, then you will see there's some bending or others lah. Okay. And other than that, this one is also explaining what will be the changes that you will see from your specimen. Okay. So initially, the profile of your stress and strain curve, the linear region, which is the elastic region, if you calculate the gradient, you can actually get a so-called Young modulus or modulus of elasticity. Okay, and the optimum point that you read over here is basically the ultimate tensile strength lah. The tensile strength optimum dekat sini. Okay, so this actually tells you what will be the maximum force that the material can withstand, and beyond that, what happens is that it will be damaged and start to become fracture. Right? So some comparison between different types of materials, and we have also looked at the plastic deformation of semi-crystalline polymers. So what actually happens if you have semi-crystalline polymers? If you actually pull the material, the folded lamellar chain will be elongated, and then after that, tilting will occur, start to tilt it, and then separation of crystalline blocks, and finally orientation of block segments. Okay. And we also have looked to these examples. And probably yesterday before we end, we actually have looked at what does it mean by modulus of elasticity. So it actually gives the value or how much the materials can experience elastic deflections. Okay, so it can be easily calculated if you calculate the gradient of your stress to strain curve. But you can also calculate that using Hooke's law, where stress is equal to E, capital E is actually modulus of elasticity, multiplied with strain, or if you rearrange it, modulus of elasticity is equals to stress over strain. And the unit is always in gigapascal or PSI. Meanwhile, for Poisson ratio, okay, so this is actually what you seen a lot for compressive stress. This one is more of, I think, tensile. When you tensile, you apply, you pull both ends. Meanwhile, for this one, it's more of like you compress the material. So that is why the gradient or maybe the plot that you will get is actually a negative plot, negative linear. Okay. So today, we just want to see the comparison between mechanical properties of a strongly bonded materials and the weakly bonded materials. So what does it mean by strongly bonded and weakly bonded? So strongly bonded means that if it actually forms covalent bonding, I mean like permanent bonding, oh, covalent bonding. Okay. So most of it, covalent bonding or ionic bonding, metallic bonding. So you should know how many types of bonding you can have. You can have like covalent bonding, metallic bonding, and whatsoever, ionic bonding. So weakly bonded normally with regards to secondary bonding. So what does it mean by secondary bonding? So this is actually more of like van der Waals, hydrogen bonding. Anything that is temporary, and this one is more of like permanent bonding. You'll see that the profile of force to separation, it's actually greater for the one that have, I think, permanent bonding as compared to weakly bonding. Okay, so the slope of stress strain plot, which is proportional to the elastic of modulus of OMOE, depends on the strength of the materials. So this one probably like if you have a metal and if you have another thing like maybe polymer, plastic or something like that, then you will see that which one actually will give a greater gradient and which one actually will give lower gradient. Of course, the one that have a greater gradient will give higher modulus of elasticity value. Okay, right. So other elastic properties. So you can actually have elastic shearing modulus. Okay, G, elastic bulk modulus K, and special relation for isotropic materials. Okay, but for this one, basically, I wouldn't ask you in detail. I mean, like in exams or whatsoever. Normally, I don't think that this one is related to us. Eh? So what is important for you guys is to understand how you can interpret the stress to strain profile, how to calculate stress, how to calculate strain. But I think like elastic shearing modulus and whatsoever, maybe this one is more materials or more physical to us. So this is just for your information, not really something for you guys to really understand. The same as this one, how you can actually relate linear elastic relationship. So it's just for your information that you have a simple tension and a simple torsion. So all these actually give you a different formula because a simple tension will give a displacement with regards to force over initial length over modulus of elasticity multiplied with area. This actually you can get, this formula you can get if you actually, derive based on the modulus of elasticity formula, because we know E is actually equals to sigma over epsilon. Since we know that sigma is equals to F over A naught, and epsilon is actually equals to delta over L naught, then if you actually rearrange this, okay, you know that this one is actually from here. Okay, so if you combine the things, like if I substitute uh, this number 1 and number 2 into A, so what will happen is that you will have like E is equals to F over A over what delta over L. Okay, so if you rearrange everything and you put like delta as the main topic or the main factor, then you will get in the end this formula. So I just want to show you like how you can get this formula based on this derivation. Okay, so the displacement of L, the sharing, so you can actually get it, with regards with the new value, Poisson ratio. Okay, and I think for simple torsion, alpha is equals to 2 ml over pi r4 g. So all this actually is just for your information, not really something for you guys to memorize. Young modulus, in terms of comparison between different materials, what you can see is as you increase the amount of, or if you obtain higher amounts of modulus of young modulus, okay, it means that the material is more brittle or more harder. Okay, so higher modulus of elasticity value, this actually will explain that you will have some hard materials, very hard materials, but in the same time, this material is brittle. Okay, so that is why you can see over here, graphite, ceramic, and some semiconductors will be having higher young modulus as compared to, of course, polymer, composite, and probably metal. Okay, right. So we are going to look for another example. A concrete pores with a 50.8 centimeter diameter is supporting a compressive load of 8,910 Newton. The concrete has initial heights of 0.55 meter. If the deformation is entirely elastic, what will be the resultant compression? So it's given that elastic modulus is equals to 20 times 10 power of 9. So what does it mean by if the deformation is entirely elastic? Anyone would like to explain on that? Fatin, Fakirah? Ada tak Fatin? What does it mean by elastic? If the deformation is entirely elastic, apa maksud dia, Fatin? Apa dia, Fatin? Tak dengar. Okay. Basically, if you have a, imagine you have a concrete post. Post ni dia macam satu support lah. Okay. Katakanlah ini rumah Fatin. Okay. Right. So you see that there's one support. Okay. Bawah ni banjir. Okay. Sini ada buaya. Okay. Ini Fatin lah. Ini sajalah lah saya lukis aja. Okay. So, compressive load. So you have a load at around 8,910 Newton. Okay. If the deformation is entirely plastic, it means that the support doesn't have any changes. Kalau Fatin duduk atas ni, siapa lagi duduk atas ni? Hanafi duduk atas ni, okay, dia takkan memendekkan. It will not going to shorten the post. Dia takkan memendekkan support ni. Okay, so it's still having the same length. This is actually the things. Length is still equal. So entirely elastic, it means that you are going to have a similar length or initial of your materials. Meaning that if you have a height of 0.55 meters, okay, even after you apply the force, it's going to be still 0.55. Okay, so what will be the resultant compression? So resultant compression, okay, you are actually wanted to see the difference of L lah, D okay. So from here, first things that you need to do is to calculate area. Okay, given that the diameter is 50.8. Okay, so 50.8, bolehlah cari dia punya apa tu area. So we know that area of a cylinder, dia punya ni bulatan ni, ni is equals to pi r square. Okay, so 50 over 0.8, okay, divided by 2, so you will get like around 25.4 cm. 25.4 cm. Right, yang ni silap ni. It shouldn't be in apa tu? cm. Yang ni sepatutnya in m. Okay. Right. So you can change centimeter into meter because we know that in this case we want it to be Newton over meter square. So 1 meter sama dengan berapa sentimeter? Berapa? Siapa tahu? Izzat, berapa Izzat? 1 meter sama dengan berapa cm?
Ya.
1 meter sama dengan berapa cm?
1 meter 100 cm.
Okay, bagus. Okay, alright. So in order to change it to meter, so you need to divide with 100 lah. So bila kita divide with 100, we'll get 0.254 meter square. Meter. And after that, you can put in the formula because what you need to do is in order, okay, to calculate resultant compression. So we are actually using this formula. E is equals to sigma over epsilon. Okay. So sigma is actually, we know, is equal to F over A. And strain is actually equals to delta over L. Or delta is also known to be delta L. Delta. This triangle ni changes of length. Okay. Right. So we are going to find what is this one, or this. So what you need to do is after you have find this one, you need to find what will be the strain value lah. Dapat strain nanti baru boleh kira dia punya tu. Okay. So from here, stress is equals to 8910 over 0.54. Sorry. Pi square. Then you will get it is equals to 44 kilopascal. Okay. Modulus of elasticity is given. So this is actually given. So now you will get delta is actually, epsilon is equals to stress over modulus of elasticity. So that is why 44 kilopascal divided by 20 times 10 power of 9 Pascal. Okay, so you will get the strain value, and the strain will actually used to be calculate your delta L, because L is actually known. This is actually equals to 0.55 meters. Okay, then after that, if you substitute, you will get 1.2 times 10 power of negative 6 M. Ada yang dapat tak? Dapat tak? So you can see over here the displacement is very very small. Kecil sangat, power of negative 6. You cannot see it. Tak boleh nampak, tak nampak beza pun. Okay. But this is actually the calculation. Alright. So another thing is on plastic or permanent deformation. Okay. At the low temperature, you will have I think a melting temperature that's bigger with the initial temperature. Okay. So what I want you to understand is that when you have materials, when it experience elastic deformation, okay, it will actually give the same profile. You will have linear, and when it start to enter plastic deformation region, okay, you will see that over here it start to have a combination between elastic and plastic, and bending start to occur. Okay, and if you release the force or unload, so you will see that the material will return with a slight changes. So this displacement is known to be plastic strain. Okay, this is actually the permanent effect. Okay, so sometimes in I think in a question you can be asked the yield strength. What will be the yield strength if given that the plastic deformation is like for example over here is 0.002. Okay, so if the offset given is 0.002, so you carry it from here 0.002, and you just draw a straight line, and whenever it overlaps with your plot, then this is actually your yield strength. So imagine that if you have a profile of ultimate tensile strength. Maybe I can copy from one examples. Sekejap, ni dia. Oh no, it's not here. Okay, so for example, if you have a material that when you test you have stress and also strain profile. Okay, if I ask you first question, so katakanlah kat sini adalah 1000 unit is actually in Pascal. Okay, 1000, 800, 600, 400. Okay, so unit from here is maybe 0.1. Okay, and then after that 0.2, 0.3, 0.4, 5. Okay, so first question, what would be the ultimate tensile strength that you can get from this material. Roughly lah, if you read. Okay. So anyone would like to try? Kamala ada? Kamala Bini?
Yes, doctor.
Okay, Kamala. So what would be the ultimate tensile strength based on this drawing profile? What value that?
900.
900, huh?
Uh,
So you just read from the maximum value. So this will be your ultimate tensile strength, 900. So Kamala say 900 Pascal, example. Okay. All right. So number 2, what will be the modulus of elasticity? This is just a rough number lah. I mean, I don't assume you to get the exact value, but just the idea. Modulus of elasticity. Anyone would like to try? Muhammad Syami ada?
Ada lah.
Okay, Muhammad Syami. So, macam mana kita nak kira modulus of elasticity? If you still remember. Kita nak kena cari apa?
Cari slope dia.
Okay, slope. So, bila kita nak cari slope, before you want to calculate the slope, you have to make sure which one is actually the linear region. So, most important thing is to note. Okay. Like for example here. Okay. We know that this actually elastic deformation region. And beyond this, start to bend, and this is actually where plastic deformation occurs. So whenever you want to calculate, it is best if you actually find the difference with the origin 0. For example, I took it from here, 200 until 0. Gradient of linear plot. So you'll get 200 minus with 0 over, maybe this is quite small, so I just assume that it's just like around 0.02 minus with 0. So you'll get a value here. Okay? Right. Number 3. So what will be the yield strength? If, let's say, offset is 0.02. Siapa nak try? No Raihan.
ya, doktor.
Okay. Raihan, agak-agak berapa dia punya yield strength tu?
700
700 700?
0.02 around 200 macam tu je.
Around 200. Sekejap nanti I use a different color. Okay. 0.02 So 0.02 maybe somewhere here. 0.02. So in order to calculate or to find yield strength, as I told you, okay, kita akan draw the line, okay, that which is actually perpendicular with your plot until it reach one point. Okay, and this is actually your yield strength. Itulah lebih kurang dalam 700 lah. Around that. right? So I think I really hope that you guys can understand this kind of extrapolation whenever you have a profile of mechanical stress to strain plot. Because normally during test or during exam, I will give one example of the plot and I want you to extract or maybe to compare the performance between one material to another. So in order to compare or to understand, you need to know what will be the maximum tensile, what will be the modulus of elasticity, yield strength, and whatsoever. Okay? All right. So I hope it's quite clear to everyone. And whenever you want to compare the yield strength, this is just as a comparison. Okay? You'll see that materials which is having completely elastic deformation are not going to show any yield strength, especially brittle sample, graphite, ceramic, glass, whatsoever. All these are actually elastic. So it says here hard to measure. So why it is hard to measure? Because we know for this kind of material, if you have stress to strain profile, it's going to be linear most of the time. So there's no like bending or whatsoever. So if you have offset, for example, so you wouldn't see any, I mean, you wouldn't fit to any overlay point. We're not going to overlay to any points. But if you have any plastic materials like metal, metal, kalau I think if the force is quite high, so what will happen is still experience bending. So you still can get the yield strength value. Okay, so similar for polymers and composite. But composite, yes, composite is still the same because composite is also a mixture between I think polymer with some reinforced material. So it will actually become more elastic. Kalau kita ada board, I think fibers or what, if you pull it, you are not going to see it going to lengthen or what. So that is why it's still performing the similar as brittle materials. Okay, hard to measure. Okay, right. So what does it indicate? If you have higher yield strength value, so what does it mean? Higher yield strength value actually it means that the material have a higher elastic properties. Okay, high yield strength. Okay, so it means that it has slightly higher elastic deformation. Okay, and this actually will give some assumption that the material have more elastic behavior, more brittle behavior. Okay, if you have a lower yield strength value, so it means that you have more plastic deformation. I think maybe properties as compared to elastic. All right. So we are going to look at this example. Example 3. From the tensile stress strain behavior of a brass specimen shown in figure, determine the following. Saya ingat I want to delete all lah dulu. Okay. Right. So determine A, modulus of elasticity. Okay. B, yield strength at offset of 0.2. C, maximum load that can be sustained by a cylindrical specimen having an original diameter of 12.88. And finally, the changes in length of a specimen originally 250 millimeters long that is subjected to tensile of 345 megapascal. Okay. So maybe we can try this. Siti Zulaifa. Siti Zulaifa ada tak? Siti. Siti tak ada. Saya panggil Siti nombor 2. Siti Norhana.
Ya, doktor.
Okay, alright. So sihat ke? Dah makan ke?
Dah.
Okay, right. So A, how you can actually find the modulus of elasticity? You just give me
Cari gradient dia.
so just give me a brief I think value lah that you want to calculate.
Set.
Agak-agak je.
150 tolak
150 tu tak apa.
kosong.
Betul? 150
Lepas
maybe
tu
150 is somewhere here. Okay.
divide by
Berapa tu?
0.02
0.02. Almost lah
minus 0.
Okay. So modulus of elasticity is equals to 150 minus 0 over 0.02 minus 0. Okay. Yield strength at offset 0.02. Siapa nak try? Tan Yun Qian. Tan Yun Qian, are you there?
Yes, doctor.
Okay, so how can you indicate? Oh man, I already give the answer lah. Okay, but yes.
380.
Okay, so from here, so we assume that this is actually 0.02. Okay, just drag here. So this is actually the point where it overlap, and this is actually the yield strength value. Okay, so you get like around 380. Maximum load that can be sustained by a cylindrical specimen having an original diameter of 12.8. So what does this mean? Anyone knows? So actually maximum load, you need to find what will be the force. You need to find what will be the force. Okay. But first, when you want to calculate the force, you need to know what will be the maximum stress. Because from here, we can only calculate force by using stress equals to force over area. Okay, so stress, maximum stress that you can get. What will be the maximum stress? Syafiqah, Najah. Berapa, Syafiqah?
470.
470. Okay. So Syafiqah cakap 470. Area? Berapa area, Syafiqah? Diameter is 12.8. Berapa, Syafiqah? Macam mana nak cari area? Area still pi r square. So pi multiply with radius. Okay, so diameter is equals to 12.8. So 12.8 divided by 2. Okay, this one you square kan dia. You get a value over here. Okay, then only you put it here. Okay, and finally you can get the force. Yep. So we check the answer. Right. Okay. Yep. Mana ni? Oh man, it's chaos. So never mind. I think maybe if you calculate that, you will get the answer. What is the answer? Apa jawapan dia tadi? Saya pula dah padam lah tadi dia punya tu. You can get the F value after you calculate the things lah, kita masukkan the ultimate tensile stress and also the area, then you get the values. Okay, right. So last question, the changes in length of a specimen originally 250 millimeters long, subjected to a tensile of 345. Okay, so what you need to do is you need to read from 345. Okay, so 345 is somewhere here. Okay, and this is actually the offset value. Okay, so to compute the change of length, because we know strain is actually equals to delta over L. Okay, so delta, as I said, is equal to delta L. Okay, so we want to find this one. Okay, strain is equals to 0.5 because the question is actually given that the tensile is applied at 345. So you get this is actually the strain value. Epsilon is equal to 0.05. 0.05 equals to delta L over 250. So delta L will be equals to 0.05 multiplied with 250, you will get 15 mm. Okay? Right. So just a few other things that you can understand from properties of mechanical properties, ductility. So ductility actually measures the degree of plastic deformation without breaking when force is applied. So percent of elongation, EL, percent of EL is equals to final length minus with initial length of over initial length times with 100. Okay, and it is always expressed as percentage of elongation. So if you want to calculate ductility, you need to know what will be the percent of elongation or percent reduction in area, percent RA. So percent RA can be calculated as area initial minus with area final, because you know every time that you apply tensile, the area final will be smaller as compared to initial, over area initial times with 100. Okay, so the importance of ductility, actually it gives indication to designer the degree to which a structure will form plastically before fracture, and it actually specify the degree of allowable deformation during fabrication process. So if you know what will be the ductility of a material, you can actually estimate what will be the maximum amount of force or amount of stress that can be withstand by the object. Otherwise, after that, the material will start to experience plastic deformation. Right. So ductile versus plastic failure. So from here, if you see material that is very ductile, it will actually forms a very sharp necking, a very sharp fracture neck. Material that has a moderate ductility, if you pull it, it will form something like I think a saw teeth pattern. And if the material is brittle, what will happen is the fracture behavior will become flat. There's no, no warning for brittle materials, if you want to fracture, there's no warning. Dia terus crack saja. But for materials that has a very ductile and moderate ductile, you will see that the material will start to elongate. So you know when it elongate, it means it start to fracture. But for brittle material, normally it's just pop, terus patah terus. Alright, so another example, okay, is basically looking at if you have a aluminum alloy test bar, okay, of 0.505 inch diameter and initial length of 2 inches. So when a level of stress of 35,000 psi is applied, a strain of 0.0035 is produced. Calculate A, modulus of elasticity, B, length after deformation of aluminum alloy, and C, if the alloy has a final length after fracture of 2.195 inches and the final diameter is 3.98 inch at the fracture surface. Calculate the ductility of the aluminum alloy. So first question is to calculate modulus of elasticity. This is actually easy because everything has been supplied. Okay, E is equals to sigma minus epsilon. So you have the stress values over here in PSI and the strain value. So you can easily calculate modulus of elasticity. And please note that over here, the unit is in PSI. So the final answer that you get is also in PSI. Right. And after that, it asks what will be the length after deformation. So you need to know what will be the final length. Okay. Given that the initial length is 2 inch. Okay. Right. So after you get this one, the how to say, modulus of elasticity, you can actually calculate what will be the length final. You don't have to use this one because we know that strain is actually equals to delta L over L. So delta L is equals to L final minus L initial. Okay. So over here, we already know that it is equals to 0.0035 equals to LF minus L naught over L naught. So L naught is basically 2. LF minus 2 over 2. Okay. Then what happened next is you will multiply 0.0035 with 2 and then after that you plus with 2. So you will get the value is actually equals to 2.007. Okay. C. Calculate the ductility. So if you want to calculate ductility, it's either from percentage of elongation or percentage of reduced area. Okay, but from the information given over here, it is actually in length. So you can actually calculate ductility based on percentage of elongation. Right. So 2.19 minus with 2 over 2, you will times with 100, you will get 9.75. Okay. And similarly, you can also calculate, if you want to calculate of reduction in area, you need to calculate the area. So over here, you need to know what will be the diameter, initial diameter, which is equal to 0.505. And the final diameter is also given here, 3.98 inch. So you will actually calculate the values and finally you get the value. So this one, I think is mistake. So it should be 0.398. Okay. Right. So from here, you'll see that the ductility percentage is quite low, meaning that the material actually is less ductile. All right. So I guess probably for the toughness and other things for the hardness test, we can finish it by tomorrow. Okay. And maybe tomorrow we can start a new chapter, I guess, because this just a few stats only. Okay. So basically, any question from the floor? Anything that you want to ask? Ada soalan ke? Okay. And probably by tomorrow, I will start to post another assignment, assignment for mechanical properties for you guys to do. I don't know whether you have any problem with your first assignment, but if you have any problem, you can contact me or you can actually ask me. Okay, so I think I will stay back for a while if there's any further question. But if you don't have any questions, so I will join the class. I would like to thank you guys for listening to this lecture, and probably we see tomorrow. With that, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.